Okay, so we are live. I hope everything is working fine. Tell me in the chat if it's good. I hope the quality is all right. Yeah, looks good to me. Looks good to me. Can read everything. Maybe I can make the font a bit larger. Let me just do that real quick. Preferences. Font. Let's change it to 415. You good? Okay, perfect. So, and let me start that donation bot I wrote last time. All right. Looking good, sounding good. Awesome. Quality is what we care about. So, yeah. Short demo, I think, for the SLP Agora, which is a simple tool to sell, but only sell SLP tokens, any kind of SLP token on the Bitcoin blockchain. So this is the thing running after I compiled it with the Rust compiler using IntelliJ, which is a pretty decent IDE for Rust. If you want to develop Rust, I can recommend it. So I already have a wallet set up here. I can show. Let's check how much we have here. Oh damn! Somebody accepted some trades I set up. All right. So yeah, basically you just press numbers to select the menu, but I think that's not the really interesting part. So we have I think the thing is it down at the moment? Okay, that's pretty bad. Amazing. Right now it worked every time, and now it doesn't. Inner map expected sequence. Yeah, maybe the data is incorrect, because sometimes the response is a bit weird. But yeah, okay, that's not good. Maybe it works. Still not working. Workspace, Bitcoin, SLP Agora, run, not in path. One second. This should go more smoothly. Okay, still the same error. Yeah, let's just have a look at the current trades in the Explorer. Where is it? I think I have it here. Alright, let's just do the requests live here. Okay. So here I have them. Where is it? I think it's down there. Yeah. 1 second. I'm using 2. Okay. So let's do the request, and here are all the trades we're currently having. Yeah, it's not the best format right now, but maybe it'll work later again, because sometimes I had that error again, then it just vanished. I don't know what happened. So yeah, we have to deal with that for now. But anyway, let's just try to create a new trade for now. I've set up a small token, TTT, Toby's Terrific Trading Token. And yeah, if it's ambiguous, because for example, if we use I think BCH3 and BCH, then you have multiple options you can choose from. Whoever made a token called BCH, and then you can select the number you want to sell. But I don't have any of that token, so we have to go with the Terrific Trading Token. Yeah, so the usage is, I think, as simple as it gets, other than crashing sometimes. You just enter the amount you want to sell. For example, let's do 2,000. This time 3,000. You want to sell, and then the amount you want to buy. Basically, like if you use a Kraken or some exchange, then it's basically the same. So let's do 100,000 for this. Yeah, and then you get a nice QR code. In this here it's white on black, but usually it's black on white, but I think that changes from terminal to terminal. And then we have to send exactly 2,000 of that token to that address. Let me check the chat. Crap dance. Oh, did we get a donation in? I didn't pay attention, unfortunately. You can see the address on the top right. Then get a crap dance. If the animation is too loud, tell me. I haven't been able to tune it perfectly. All right. So yeah. Okay. So I set up. Okay, send this amount to this address. Now we go to my wallet. My Electron Cash SLP wallet, so it has to be the SLP version. There I can send the I just paste the not the QR code, the simple ledger address. Add a nice sell, add a nice description. Sell for 100,000. That's 10,000. Did we use? Yeah, 100,000. And then the amount, which is 2,000. This has to be precise, because otherwise it might be unspendable, because like the contract says 1,000 and the amount in there is 2,000, and then you either have to burn the coins or it won't go through. The trade will be an invalid or even unspendable transaction. Okay. And then we'll send. And yeah, we'll get the transaction in pretty quick. That's the good thing about the Bitcoin Cash network. Everything's pretty quick. And yeah, this is the, yeah, we can have a quick look what is generated. So we got two transactions, actually, two transactions. This is the transaction we just made here in Electron Cash. Yeah, it's still up. That's the same hash. This is the one we waited for to be sent. And this is the trade listing transaction ID. It's because tokens can't have any metadata. So if we want to say, okay, this is a trade, please send it, we can't have any data in there that says that. So we have a separate transaction which basically says, okay, this is an exchange, give me money and I'll send you, and you can receive the money if you spend that amount to exactly that address, and we'll cover that a bit later. So maybe we can buy now. Okay, still not working. I fixed that. I fixed that later. I have to have a look what's going on there. But the query seems to work fine, and yeah, maybe one of the requests here fails, or maybe they changed the API mid flight. But yeah, if it works for you, that's good. Okay, so let's go a bit more into the nitty-gritty details. So when I requested, okay, I want to send this token with this amount, with this buy amount, with the sell amount, with this buy amount, then it generated a smart contract for me. We can see a small outline of the smart contract here. It's right. No, not here. It's right here. Yeah, it's basically if swap, and the important part is here the check sig verify and the check data sig, which basically enforces the contract on the transaction that's trying to spend. But yeah, we'll get into that later. But let's continue with the more higher level overview, which is still pretty technical, but yeah. So let's have a look at the first transaction, the transaction I made with my Electron Cash wallet, this one here. Yeah, it's basically just, okay, now it's gone, but we can have a look in the Explorer. I will pick the Bitcoin Explorer because it shows the, it's just very nice for SLP tokens and OP return stuff. So can we see this? No, okay. Yeah, okay, yeah, pretty good. We'll see this is a normal SLP transaction, so it has SLP, it's sending, and then all the metadata that's required for SLP. And we'll see 4 outputs in total. This is the the metadata of the SLP transaction. This is the smart contract, 2000 trading tokens I've locked in there. The amount is the minimal dust amount. Like for every simple ledger output, it's always the dust amount. And here's the return address. So this will be sent back to my wallet here. So we saw 2000 down. Maybe we can, yeah, we see exactly that. This is probably yeah, this is hex. Let's stick with what we see here. Okay, so 2000 sent to that address, which is the one that was shown here, PZ5RK. PZ5RK. Yeah, and this is the remainder of my wallet's complete, like this is sent back to my wallet in Electron Cash. Okay, and this smart contract, we can have a quick look at it again. It basically, if we, this is the spending one, it basically just, okay, yeah, it takes 6 inputs in total. The public key, serialized SIG, and these 3 things. So this is the signature, this is the public key, and which, by the way, can be like they can be random. So we can just pick any private key and public key, private public key pair, and sign the transaction with that. But we'll get into that later. Then the pre-image, which is basically the thing that's being signed. We feed that into the transaction, but only the beginning and ending part, and in the middle there will be the actual outputs of the pre-image, which will be checked if they actually match the real outputs. So we'll feed, and these outputs here are the remaining outputs. So this contract actually only enforces the first 3 outputs. The first output has to be a specific OP return, a specific SLP output. The second one, maybe you can write that down here. So the first, that's a selection tool. Where's the pen? So the first one has to be a OP return. This is a bit laggy. Turn, which is an SLP. And in our example, it enforces that the first vout is like in the SLP protocol. It has to specify which output receives how many tokens, and in the first output it has to be, I think it was 2000. No, actually in the first output it has to be 0, because that's our address where we want to receive the money to. And yeah, and that's it actually. So we only have no, and the second one, no, that's not it actually. The second one, that's the 2000. So, and then here the second one, okay, the second output, maybe I should be consistent with the counting. Let's do 0-based indices. Okay, 0-based indices. So the 0th output will be the OP return with the SLP, and the first output will be which is enforced, is the address of our BCH address. The one which is in this wallet. In my wallet. No, not this one. Here. And this one. So this is this address. So it enforces send this money to this address. BCH address of how do you say, offerer or seller? BCH address of seller. And oh yeah, I mixed it up. So in SLP, the indices are started by 1. So let me just fix this real quick. Okay, and change them to 1 and 2. Okay. So this is the thing that is enforced by the contract. It says SLP and BCH address of seller. Now you're saying, okay, what about like the receiving token, because this is only one output, and the contract actually allows an arbitrary number of outputs afterwards. So it could be pay to script, pay to hash. If we had SegWit, then that probably would work too, but we don't, so it wouldn't. And so any outputs, the seller, the buyer likes. So yeah, and he could burn the 2000 tokens and stuff like that. But the thing that is enforced is the first and the second output. Okay. So yeah, and then this generated script, which as input has it has almost no inputs. Hello, Claudio. No, Claudio? I don't know. Yeah, exactly. It has two inputs: the start of the outputs, which is this output and this output, and the cancel address. Here, currently in the implementation I made, it's not possible to cancel trades, but that's not really a problem because you can just buy the tokens yourself, and then you have you can keep the money because you send it to yourself, and you keep the tokens because you also send them to yourself. So it's not really that bad. But if you like send the tokens to a like way too high amount that you don't have right now, then that might be okay. Still not working. That might be then it might be necessary to cancel. But yeah, I added it in, so if there's an issue, we could cancel the trade manually. So yeah, so the only, like in a ordinary in a pay-to-public key hash output, which is a Claudio. Okay. The only like variable we have is the address, the public key hash, the address. And here we also only have the cancel address, public key hash, and the outputs pre. So pre is the start, the beginning of the outputs. Okay. Does that make sense so far? Let me get into how the how the second transaction works. No, I deleted it. Well, I think, yeah, let's just do a new one. I mean, why not? So let's create a new token trade again with my and now let's do this amount, 1,500, and we'll do 50,000. So we sell 1,500 TTT, and we want to receive 50,000 satoshis in Bitcoin Cash, and we'll send to this address the smart contract address, exactly 1,500 TTT. See, my name is a bit too long here. Send, enter my password. Oh, I think there's a donation going in. And payment sent. Okay, now let's go back in here. How many satoshis is that? 1 million satoshis. Wow, thank you. 1 million satoshis. Thank you very much. Yeah. Okay, so we can have a look again at this transaction, just to be, which is basically the same as this transaction, but with a different amount. So again, we see the 1,500 TTT, the remainder, the back to wallet. This is also back to wallet, and this is the SLP. Louder? You sure? How much? I'll do it a bit louder. Can't if it's not. Okay, we see it for a short time just to make it. And it's gone again. Okay, yeah, it's a bit louder now, but only a bit. Okay, so the next transaction is this one, which is sent right after we received the transaction. So this is funded by the internal wallet, by the wallet which is like managed by my app. Okay, so let's check that out, which is it's like it's pretty different from the other transaction, from the SLP transaction, because this is a this has like this exchange lowcat ID. So the first 4 bytes in an OP return transaction is called lowcat ID, and SLP basically has SLP 0, and this has exchange EXCH, then, which is basically a new type of OP return output. Then it has, we can this is not correct, we can have a look at these outputs here. Then it has a version which is currently 1, but there's another donation coming in. 780,000 satoshis, thank you. Then we have then we have like the trade type, which is currently sell, and as far as I can tell, the only way to sell to trade tokens provably on chain is by selling them, except if we make more advanced tokens, but I'm not sure if we want to do that. So yeah, let's check it here out here again. So we have the exchange string, we have the one string, we have the sell string, and then we have this transaction, and you might remember that transaction. No, wait, here. Oh yeah, okay. So this is little endian encoding, and the Explorer wants big endian encoding. But if we paste that somewhere where we can read it, let's paste it just right here. If you like reverse every 2 bytes, then you can see it's the same. So 78 F9 177. So yeah, this is I should probably change. That's an artifact of the implementation. I should probably change that in version 2, but that's not much of an issue. So after that comes the output index. Got to run, but I love that you're doing this live streaming. I have a feeling a lot of JavaScript developers will watch this recording in the future. I think a lot of people will be trying to copy the script in the future. Would be great if you can go into detail on the opcodes. Yes, I will definitely go into details with the opcodes. Yeah. So I'll go into more detail of the layout of the transactions first, and then we'll do the opcodes, which is the innovative part, more or less. Okay, and after the okay, so it's rehash. We got the exchange string, we got the one string, we got the sell string, then we got the transaction ID in little endian format. Then we got the output index, the sell amount, and the buy amount right after each other, encoded as big endian numbers, like 32 for the output and 64 for the amounts. Then the receiving address and the cancel address, which in my implementation is always the same, but the implementation allows basically they can be different, like if you don't want to use the same address here. Okay, and that's it. So if a transaction is on the blockchain, which has this structure, then anyone can be like, oh, I want to buy that transaction. Then he looks up this transaction, which is not this one, but this one. He looks up exactly this transaction. Sees, oh, hey, this one is unspent. Because if it's spent, then the trade obviously has been accepted already. Then he crafts a transaction which contains the 4 things I laid out previously. Those 4 things. 6 things, yeah, 6 things. If he wants to spend them, then he has to push this flag at the end. If he wants to cancel, then 0. And then he signs all the whole thing, and broadcasts it to the network, which currently isn't working. Yeah, still an error. Yeah, maybe I'll fix that later on stream. Okay, so, and yeah, that's the thing. Let's have a short look at how a trade would be accepted. At the end, it is right here. I created a pretty nice library API for creating transactions, creating, signing, all this stuff. So it's actually pretty easy to use if you want to create like your own enforced outputs. So let's go through that real quick, so you know how to how this transaction is actually created. So yeah, so we got all the input from the user. We had all the, okay, what token do you want? Where do you want to send the tokens to? Yeah, so we this is the token ID, and we have two outputs which we have to feed into the smart contract. So the first output is the SLP send output. So we send SLP send output is like the whole the entire send instructions. So it says, okay, the first output quantity is 0, because this is actually where we want our money to go to, and we don't want any tokens back. And the second one is the sell amount. So the full amount we've put into the smart contract will be sent into the second output, the second starting by 0. So the first output obviously will be the SLP output. Yeah, and then the second, okay, so the second output, which will be fed into the smart contract, counting by 1, is that we actually receive the money. Because to be fair, we don't really care if we don't really have to enforce that the buyer is actually receiving the money. I mean, he could like just burn the amount and not send it to the second V out. But I think it's nice to enforce it, because if you mess up, if you swap the like if there's an error in the script, then it will burn the tokens or send them to the wrong address. And this enforces, okay, they can only be sent to this output. So then those two outputs will be put into this enforce outputs output. So that's a pretty weird name, but it's basically an output which enforces certain outputs. Yeah, the amount enforced, where does it come from? It's probably the trade amount. Yeah, this is yeah, I think it's just the dust amount, so it's not really important. Okay, but the two important parts are these two. So it says, okay, the first output has to be this SLP output, which is, if we have a quick look, oops, it's basically just a OP return thing. This thing, SLP token type send, nothing too crazy. So if you read the SLP spec, this is like the way you do an SLP send transaction. So after that, there's the cell amount output cell amount. Yeah, this is the amount which will be sent to us. So this address will be entered by the user, and it says, okay, send me the tokens I just bought to this address. And the fourth output, so these two aren't enforced. The fourth output, okay, the fifth counting from 0, is the output back to wallet. So for the stuff we like for the satoshis in our wallet, we will send them. We need them for signing and paying the fees, but we'll send them back to where they came from, so back to our wallet. Yeah, so the next thing is generating getting the inputs. So here we'll have 4 parts: outpoint, a sequence, an output, and a key. The outpoint is basically just the transaction we had a look at earlier, which is the this transaction right here. No, this transaction right here. And specifically this output. So this is the outpoint of the smart contract transaction. Of the smart contract. Yeah, this is the outpoint of the smart contract. Sequence is always this number, and then we'll have the pay to script hash output, which we need for the signing and stuff. And then we'll have a random key, not a random key, but like an arbitrary key, so we can put anything we want there. So we can put like a Ron Paul quote in there. Like it doesn't matter what we put in there. And it can be public. It's like it doesn't have to be secret. After that, we put all our outputs together, do the size estimation, check if it's if the wallet has enough money, enough satoshis. Then we'll sign the whole transaction for real, and then we will either send the transaction or we will encode it and print it on the screen, because maybe the user wants to inspect it before sending it manually via a broadcast, transaction broadcasts tool thing. Let me drink something real quick. Okay, so this was the way how to spend the smart contract. But let's actually go into how the smart contract works, because it's not really easy. It's pretty complicated, but also pretty smart. Like I think Payne Summer, someone named that name, came up with that idea. Then I expanded on that. And yeah, so let us, I think I sometimes use paper. Yeah, I've written it down here, but let me transcribe it for you onto GIMP. Oop. Does it work? Let's just get rid of it. Okay. Fill like this. Oh. Huh. Okay. Maybe we have to move it down. Okay. Fill it with white. Okay, no. I'm used to Photoshop actually, but I only have GIMP here. So, okay, so the opcodes are, I will just write them down and just tell you in abstractly what they do. It's a push of the outputs pre, out, oh god damn it, out, this thing's a bit laggy, out, puts pre, then we have OP swap, which will swap the two items on top of the stack. Yeah, if you're familiar, as a short side note, if you're familiar with Bitcoin scripts, it's basically a stack automaton. So you have a stack, you put stuff on the stack, and then you can do operations on that. So for example, swap is if you have AB on the stack, then after you execute swap, it will be BA. So if you read from below, yeah. And after OP swap, we have what do we have? Cat. I will just write them down real quick. We have cat, then we have hash again. Oh yeah, cat just concatenates the two items on the top of the stack. Then we have hash, which will hash the top output twice with SHA256. Then we have another cat, which again will concatenate the two top outputs. Then swap, which we already had. Then cat again. Then a single SHA, which is for the data sig verify. SHA256. Running out of space. So then we have a free dupe, which will duplicate the top three things on the stack. Then we have a drop, which will remove the top thing, which will remove exactly one thing on top of the stack, if there's one. If not, it will fail. Then we have a push, which will just put the next thing on the stack, which is actually this number here. We'll push for like 0x41 hexadecimal on the stack. Then we have another cat. Yeah, let me just continue over there. No, I think we can. We'll manage. So this continues here. Then we have a swap, which will swap the two items. Then we have a check sig verify, which is like an old opcode. This is not the new one, which just verifies the transaction works. Then we have rot, which rotates the first 3 items around. And then we have check data sig, which is a new opcode which was released recently. So why this contract? This looks pretty crazy with all the swapping, cutting, dropping, duplicating, then dropping. But I think I can't prove it, but I think this is a very short encoding of the contract. So if we have a look at this, yeah, let's go through the stack. If we have a stack, so yeah. Okay, so the first 6 things that will be executed of the smart contract are all the push operations of the inputs. So we'll push these 6 things onto the stack of the smart contract. So let me move that up here, otherwise I will forget it. So the first thing that will be pushed is the public key. Then there's the signature. After that we have the pre-image beginning, I call that P1. Then we have the beginning, the end of that, and then we have, I can scroll around with that, that's pretty buggy. Then we have the outputs, outputs end, out end, so yeah, as a quick reminder, these two are basically an arbitrary, this is basically an arbitrary public key which verifies the signature, and this signature has special properties which we'll see later when we go down the stack. So yeah, and this one is all the outputs the user wants to have, the spender wants to have additionally, because as we see here, outputs pre, outputs end, so outputs pre, outputs post would be maybe a better name. These are enforced by the contract, and these are not enforced by the contract. These can arbitrarily be chosen, as long as they don't violate the Bitcoin rules, because then the transaction will just be invalid. Okay, so but let's just execute that contract. We'll push the outputs pre onto the stack. Oops. Puts pre onto the stack. Let's just use out pre. So we have those two on this is the top of the stack, this is one below, and so forth. And then we'll have OP swap. So those will all be keep the same. They will continue to be the same. and then those two will be swapped. So we have out pre and out end, and then we will concatenate them. So those will remain the same. Oops. Oh, one moment. Okay. And these two will just become one thing, which is the entirety of all the outputs. All the outputs will be just one thing. So it's basically outputs. Outputs. Oops. Yeah, I think we're a bit misaligned. But then we will hash the outputs. And I'll show why that is when we look at the pre-image, which we'll do afterwards. Yeah. Okay, so this will be the hash of outputs. Outputs. Yeah, so this will be the double hash of the outputs. Let's maybe do squared. Yeah, after that we will concatenate these two things. We'll have yeah, we will concat them like this. So just use the, let's do the Spenden notation, which is just a dot, and then we'll have a hash of outputs. Oh, god damn it, this tablet is pretty bad. So this should say outputs, but it doesn't. It sometimes just makes a dot. Output, and this should be an S. And then we will swap those two things around, which I'll just make like this because I don't want to repeat everything over and over again. And then we will concatenate all of them, which will actually give us the pre-image. Pre-image, which is the thing we will sign in. No, the thing that's that will be built by the node to verify that it has the that the transaction actually is signed correctly. But we'll get into that in after we finish this this script. Yeah, we'll get into that after we finish the script. So we swap, we cat, then we have the pre-image, and then we single hash only once. We single hash the pre-image. So we have h pre-image. Yep. And after that, we will do a 3-dupe. So we'll have these will keep the same, and we'll have a copy of the public key, a copy of the signature, and a copy of the hash pre. Let's make h and 3 dots. Dot dot. Same thing as here. I don't have Photoshop installed at the moment. Then we drop. So we'll just have those 5 left. And now comes the interesting part, or the more interesting part, because currently it was just shuffling around stuff. After the drop, so then we concat the this 41. We get into that shortly, but it's this thing is only needed by check sig verify. It's basically the type of signature we're having, which was introduced basically as a hard fork by Bitcoin Cash, like the first hard fork, the very first. Yeah, after that we concat the 41 to the signature. Yeah, I'll like this swaps stuff around, but it essentially, so let's make ... essentially concats the signature with with 41 in hexadecimal. So this will be this no. Yeah, it will, these two operations. Then we will swap the top 2. So we have the sig 41 and the public key. This is an S, not a P. Public key. And then we will do the check sig verify, this here. And this will pop the top 2 things off the stack. And if they're like correct, or if they sign the current transaction, then nothing will happen. But if they don't sign the transaction and they fail, then the transaction will be invalid and the script terminates immediately. So this here ensures that all the actions here on top match with the current transaction we're having. So we did all these things just to make sure that this here, that all of this is actually what we have in our current transaction. So we check that the end of the transactions are actually the outputs we have in our transaction, that the start of the transaction is actually what we have in the start of the transaction, and that the start and finish of those 2 are actually part of the transaction. Yeah, but that's not enough, because we currently didn't enforce anything on this on the signature itself. So if you were to have a look at the operations, so we can clearly see, like here there's like all these things going on, but there's nothing happening with these 2. These are just like completely, they're just doing their own thing. And here we're just duplicating them and just checking them, just checking if they sign. So this is basically so far it's basically anyone can spend transaction, it's just a bit more fancy. So to actually get it to do the signing, we'll have to do the check data sig. Yeah. So after the check sig verify succeeded, we'll only have these three things left, which, as a reminder, is the public key, the signature, and the hash of the pre-image. Hash dot dot dot. And those are currently not in the right order, but if we do a rot operation, then they will be in the right order. So this will put the signature on the bottom, then the hash in the middle, and then the public key on top. Yep. So, and then if we do check data sig verify, then we actually enforce that this signature, which currently could be anything, actually matches the things we put on the stack. Okay. And after that is finished, we will have a true on the stack. So this will be afterwards, it will just be 1 true. And if it and if like anything of that failed, so if what we put here doesn't match, then it will have failed already. Then the transaction will be invalid. Okay, so let's just get shortly into how this pre-image thing works. This is pretty simple, I think, more or less. So this is BIP 143, which explains it. This is actually for a SegWit, but we use the same signing, just the Zcash type is different. But that's just a side note. So the pre-image is those things here, those 10 things. And most of them are pretty simple, like the version, the out point, which is basically the transaction that's being spent, script code, which is the code of the output that's being spent, the value is the value of the output that's being spent, and stuff like so. It all contains information about the output that's being spent. You're welcome. Yeah, see ya. And yeah, the outputs, the log time of the transaction, which I think is useful if you use the check log time verify opcodes. And the interesting parts for us, the interesting part for here is only this part here, the hash outputs. So everything before here is everything before is irrelevant for us, and everything after here is irrelevant for us. And actually, in the implementation I made, these can be freely chosen by the spender of the transaction. Only this thing right here is like limited, like not like it has. Only this thing has a constraint. Everything is unconstrained, and this hash outputs is actually all the outputs concatenated, just like output, and then you hash it. And this is exactly what we do here. Maybe make this a bit smaller. Does it go? Okay. Ah, okay, we still had some space. Anyway. Yeah, which is what we do here. So we have the beginning, which is enforced. So it's pushed here. It's written. It's basically hard coded into the smart contract. Then we have all these inputs. Then we'll concatenate the two outputs, and then we hash them. And then we have this beautiful part right here, hash outputs. And after that, this is 32 bytes. After that, we will just put this one right in front of it, and this one right behind it. Like these are the two cat operations. No, these are the two cat operations. So it cats the beginning. Yeah, I think the number 2 is misleading. It actually should be 1. So the first part is catted at first, and then the second part is catted behind. So yeah, this basically pads those two things before and after. Yeah. And after that we have our pre-image, which is this thing here. And the way we did it here, it is exactly the same as we did in the specification. That's why we can reuse the signature twice. So we duplicate it literally here. And if like this one signature matches both the check sig verify and check data sig, then the pre-image we have fed in and the pre-image we actually have for the transaction are both the same. Yeah. And that way we can enforce the outputs. Yeah. All right. Let's just have a short look at the code again, just to show how this is actually implemented. Have a quick sip. Look. Okay. Yeah, because actually I kinda lied here. Oh, where's it gone? Okay. Because this here is not the full script. There's actually this cancel around, but this here is exactly what I just wrote down, but in a bit more readable fashion actually. Yeah. So the way it's implemented is by creating this trait. Should I go into the trait system that I made? Yeah, maybe real quick. If you want to use this yourself, this might be very useful, because it's very easy. Like there's so many different kinds of outputs you want to have. You have like I think they're all here, aren't they? No, they're in outputs here. You have pay to script hash. You have this thing that were tested. You have OP return. You have SLP. You have this trade offer. You have enforce outputs output, and you can add many more, like anything that works. Maybe you can do a memo output, because like this outputs sends a memo. Or maybe you can do some other kind of trait which will be enforced by this thing. And the output is basically just, okay, how much are you sending? What is the script that will be put into your transaction? What is the script that will be signed, which is sometimes different for, but only for public, for script hash. So pay to script hash transactions, and then this will actually sign or build the sign scripts given the signature, public key, and stuff like that. Yeah, so if once we have those 4 things, the signature script will be actually pretty easy. Where is it? No, it's here. Damn it. Signature script here. Yeah, more or less easy. So we'll get the serialized signature. We'll build the pre-image here, the pre-image begin and the pre-image end. The pre-image begin has these things. So everything up to hash outputs, as you can see, that's version, pref outs, hash sequence, out point, script code, value, and sequence, but not hash outputs. And then the post thing will have exactly the mirror image except hash outputs. So all of those will be false, and the only last things are log time and sig hash type. After that, we go through all the remaining outputs. So enforced outputs is the ones we have to have, and the last ones we have to say, okay, we want to actually spend. These are the inputs for the smart contract. We actually want those outputs to be spent, and after we put them into the vectors, we put them into a script and return the whole thing, which is then put into the transaction. And that is basically it. Yeah. Do you have any questions? Do you want me to go into details some more for some other stuff? Or should I like answer stuff more on the Reddit maybe? Yeah. All right. So it seems like none of you have any more questions. So I will, yeah, I will end the stream here. All right. See you guys. Have a good night.